number 2, carboxylic acids, and this time you don't get to see my smiling face because I really watched the video and decided that I wasn't really smiling very much. Anyway, no, that's not why. Just carboxylic acids it is. Alright, so carboxylic acids, you know this, they contain the carboxyl functional group. And then we've got carboxylate ions, and they're containing the C double bond O minus functional group, which makes them really easy to name. So there we go. We've got ethanoic acid. We've got the ethanoate ion because we've got 1, 2 carbons. Now we've got some really nice. This is the pretty picture version, the coloured version. I looked up why caproic acid is called that, and because apparently, no, maybe it's caprylic. Must be that as well. It smells like goat, apparently, so that's why it's called that, and it means goat in Latin. So, smells like goat means goat. I figure that I can probably look up one of these every year. I teach it, so then by 36 years, I'll know them all. It's a good idea. All right. So, carboxylic acids, you also know this, are produced by the oxidation of primary alcohols. So remember, we oxidize primary alcohols in the presence of acidified potassium dichromate and heat, and we form aldehydes. If we keep reacting that, if we don't distill off the aldehyde straight away, it's going to continue oxidizing to form the carboxylic acid. It requires heat to proceed at a reasonable rate, otherwise you're there all day. Now, being an acid, they do, to some extent, ionize in water, and you do have to actually be able to write these equations out, specifically with their reactions with hydroxides, carbonates, and hydrogen carbonates. They're weak acids. You know this with citric acid. It was a weak triprotic acid. So that means that they only partially ionize in solution with water. In water, remember they're fully ionized in the presence of a strong base, but in water, and that's what we talk about here, they're only going to partially ionize. So that means in terms of equilibrium, that the equilibrium is actually lying to the far left, meaning that the forward reaction is not really favored. So we're going to have a bit of this forming, but not a lot in water. So let's look at the reactions with the different things that we have to know. If we react with hydroxide ions, we simply form the carboxylate salt and water. Now this is leaving off, for example, sodium, which would be here, and would therefore also be in here. We don't need that, so we're not including it. If we reacted it with carbonate ions, we would also form carbon dioxide, same with hydrogen carbonate. Okay, you do need to know these polyatomic ions, so please learn them. Now these reactions are exothermic. They do occur fast at room temperature, so they don't need, for example, extra heat to be added. When we produce CO2 gas, we will see effervescence or bubbling. So as we go through, you should be building for yourself a little toolbox of tests that we could use in order to be able to distinguish what the different things that we're working with are. And so in this case, we could be adding in carbon dioxide in order to see the presence of effervescence, because that would indicate that we have a carboxylic acid present. Now, if we then talk about the salts, and remember we did talk about how you form the salts. If you react and oxidize in the presence of a base, you form aldehydes in the presence of a base, you form a carboxylate salt. Here is our carboxylate salt, and here is a cation. Now, that could be something like this, or that, sodium, or potassium, but different metal cations could quite easily react with the ethanoate. We've got 2 carbons, so ethanoate. So sodium ethanoate, potassium ethanoate. Now, these are soluble in water because they're ionic compounds, and you should remember this from last year. If you have an ionic compound, you can undergo ion dipole interactions, which, remember, are the strongest secondary interaction. They are actually stronger than hydrogen bonding because the ion, a full charge, is interacting with a partial charge instead of 2 partial charges interacting with each other. So here's our full negative charge interacting with our partial positive charge, forming an ion dipole bond, which is quite strong. Now, carboxylic acids can only form hydrogen bonds with adjacent water molecules. They can't form ion dipole bonds because they're carboxylic acids, they have no charge. These are weaker intermolecular interactions than ion dipole, because the charge on an ion is much stronger than the partial charge on a dipole. So therefore, a carboxylate ion is going to be much more soluble in water than a carboxylic acid. So dipole-dipoles, weaker intermolecular, ion dipoles, stronger intermolecular. So if we've got those large organic molecules with significant non-polar chains, but a carboxylic acid functional group, they're still likely to be insoluble in water. But if they form a carboxylate salt, if they're made to form the salt, then they can be made to be soluble in water. So with drugs, for example, here's acetylsalicylic acid. That's aspirin. There's a carboxylic acid group there. It's an ester group over there. That's insoluble in water. But when we have the exact same form as the salt, it's got this full charge here, so it can form ion-dipole interactions, and it's actually soluble. So when we have drugs that have carboxylic acid functional groups, we often take them as a carboxylate salt, because that ion will be soluble in water, and therefore the drug can be transported in the blood, which is really important.